Okay, so I was recently asked a question as to the impact that alignment has on the accuracy of measurements. So to answer this question, I first decided it would be a good idea to seek out third parties so as not to offer up a biased opinion and certainly to try to answer this in a scientific fashion. So the first thing I did was I went out and found a user guide for another software product out here, SWARP, and in their documentation they have a section which is entitled Skeptical Sam's Questions. And one of these questions is, it starts off as, I am the kind of guy who does high precision astrometry and photometry. My sources are detectable in raw frames. Resampling would just wreck the signal, so I prefer to combine measurements from individual images than to co-add pixels. And this is very much related to the idea of alignment, which also does resampling. So it is true that the answer here, posed by the author in this documentation, is it is true that resampling distorts slightly both signal and noise. However, if done properly, and if the data are not undersampled, then the degradation is generally very small. So as one example, resampling a single ground-based image with atmospheric seeing of 3 pixels, conversion factor to 2 electrons per ADU, twice with the SWARP program, and comparing fluxes and positions measured using PSF fitting, one would get for bright stars RMS differences of less than 5.10 to the -4 magnitude and 10 to the -3 pixel between the original and twice resampled images. So this is said to be already much better than what photon noise allows for. So apart from situations of strongly non-stationary noise or undersampled data, the consequences of resampling are expected to be negligible. So here is just one third party answering this question in a roundabout fashion, but basically the summary here is that there should be negligible impact. In fact, it should be less than that of what photon noise allows for. In other words, you should not see any noticeable difference. Now, I will not stop here. Obviously, what we would want to do is then evaluate this further. So one way to do that is simply we can take some data and we can compare with the measurements taken in another program that presumably does not do this alignment, and one here that does, which is Tycho, and evaluate and compare how this works. So to do this effectively, it's a good idea to work with data that does depend on high accuracy photometric observations. So an exoplanet is a good candidate for this. So I have previously done a video on an exoplanet, but here it is, I'm just going to go through the whole path and just go ahead and try to answer this question. So here again is a data set that is available online. So if you go to astrodennis.com, he provides scienceimages.zip as an archive file, as well as calibration files for that. So what I am going to do is I am going to run through this data set and process it in Tycho using the alignment routine, and then generate photometry measurements and see that we are still able to achieve the high level of accuracy needed to generate the results for this exoplanet measurement. So let's go ahead and take a look and see how that performs. Okay, so the first step is to load in the raw images. So I go to List, Add Images, and these are the raw files here, as you can see, pulled in from that Science Images archive. So select all the images. There are 336 of them. They are each 45 seconds in duration for a total exposure time of 4.2 hours. So at this point, these are the raw images. So what we want to do is calibrate them. So you can go to Action, Calibrate Images, and I am going to use the dark and flat frames that were provided in that data set. So I'm going to go ahead and click OK. And this will proceed to perform the calibration process on these images. And then the next step is to perform the alignment routine. So now that they have been calibrated, I'm going to go to Action, Align Images, and I'm going to use the internal alignment routine. If you wanted to update or modify the settings, there is a tab for it here. So number of threads, bicubic interpolation, downsampling of 4, normal mode, those are the settings that I am using. So I click OK, and it is going to proceed forward with aligning all 336 images. So we will go ahead and give it a moment to do that. And once this step has finished, then the last step before we do any photometry work is to plate solve the data set. So it has just now finished aligning. Now it is saving the results. So now we can go to Action, Plate Solve. So I'm going to use the online solver. It is very quick because it does not actually upload the image data, it just uploads extracted sources from the image. You can specify a lower and upper bounds if you want, downsample factor 4. So these are the settings I am going to use. So I click Start, and it has already extracted the sources, uploaded them to the online solver, and now we are checking on status. So it has started the solution, and now it says solution has been found, verifying it, and now it has finished. So we have now, at this point in time, completed calibration, alignment, and plate solving. So now we can go ahead and go to Action, View Images. So this loads the images into memory, and now we have the image viewer open. And if we want to, we could go ahead and we could do display catalog stars that will overlay these blue squares onto the image, and you can see that this is a good plate solution. But what we want to do is we want to basically proceed with the photometry aspect of this. So we want to take measurements of our target object. Now, the target object in question, this is WASP 12b, is the exoplanet. And if you're not sure where it is in the field of view, this happens to be considered the host star happens to be considered a variable star. So you could go to Photometry, load variable stars, and that is going to go out to this service here, and it will then display the known variable stars in the field of view. So as it happens, WASP 12 is one of those. So you can click on it, and it centers it in the field of view. So this is the host star, and the idea here is that the exoplanet, the signal from that exoplanet should be measured. It should be possible to measure that signal on these 336 images. So that's what we're going to do. We've taken basically a data set that has 4.2 hours of exposure time, and it should be possible to indeed observe that variation in magnitude. So what we want to do now is go ahead and set up the comp stars. So there's basically a whole lot to do with photometry that I'm not going to get into, but this is going to be differential photometry, and the idea here again is to try to match exactly what was shown in this tutorial, this practical guide to exoplanet observing. So again, what we're saying is that we should be able to get the exact same, or at least very comparable results with Tycho as we do with another program. So the program that was used in this guide was AstroImage J. That's a very well-known photometry program. And here what we're saying is we'd like to compare results that were achieved with AstroImage J with results that we achieved with Tycho. So basically, again, what we want to do is use the exact same settings. So comp stars, as it happens, he wound up using 3 comp stars. Now, if you read it initially, basically had 4 comp stars, and then he whittled it down to 3. So if we have an image here, you can take a look at this. So the green is the target, in this case the host star, and then the red, those are the comp stars. So if I were to zoom in here, you might see that better. But again, that's our target. So if we look at that here, that is indeed the host star. And then the comp stars here, he had 4 of them initially again, but then he actually got rid of this one. So what I'm going to do is just replicate that. So this is C2, C3, and C4. So I can go ahead and do that here. So C2 is right here. I can add to active comp stars. And then C3 is right here. I will add that one. And then finally C4 is over here. So add to active comp stars. So normally if I were doing this on my own, I would use the find comp star module. And that would basically help me identify what comp stars I might want to use in the data set. But again, I want to use the exact same settings, exact same comp stars, so that we can achieve very comparable results. That's the idea. So again, the question is, does alignment have any measurable impact on the accuracy of the measurements? So that is the question we are trying to answer. So again, if I wanted to, I could generate data on these comp stars just to make sure that they are not variable stars, but even if they were, I would still use them because that's what was used in the guide. But as you can see here, they look to be pretty consistent in the presentation, that these are not variable stars or anything of that sort. So the next step then is the photometry, the aperture settings. So he mentioned in his guide that he was going to use aperture settings of 9 pixels for the inner radius, and then 16 and 24 for the inner and outer of the background. Now, as it happens, that actually, if you actually go down to his results here, his final settings were 13, 14, and 29. Now, Astro Image J uses a different convention for its aperture settings. So the first setting here is 13, which is what we want. That's the aperture, the inner, if you will, radius one. And then what we have here is what's considered a dead zone followed by sky annulus. So this works out to be that if you've got 13 followed by 14, then the dead zone is just 1 pixel. So you're basically taking 14, subtracting 13, you get 1 pixel for the dead zone. And then 29 minus 14 is 15 pixels. So that's how you would convert to get a comparable aperture with the Tycho software here. So again, that's what that looks like here. If I wanted to zoom in, you could see that. So that's a fairly large aperture, but again, that's what he wound up using. Again, if I wanted to, I could double click on that host star here. And so that's what we've got. Again, just trying to get exact same settings that he has here. So with that in mind, we now have our comp stars, and we also have the aperture settings. So the next step then is to go ahead and define the markers. So if I double click on that target star, and I can zoom in and then say create markers 1 and 2. This goes back to Tycho originally was developed for moving objects, so you could define marker positions. In this case, it's a stationary object, so markers 1 and 2 are on the same region in the image. So I've already defined marker 1 and 2 here as this object. Then I can right click and choose create photometry for markers. So it's basically going to create measurements for each of these 336 images. And it's already finished. So here we have, again, this is the window of measurements. So there are 336 of them. And if we wanted to, we could go ahead and plot the graph. So I can go to graph, plot all sets. There's only one here. And you have this presentation. So you can already see this, basically this change in magnitude of the host star as the exoplanet enters and exits the transits. So so this is inspiring that we are able to achieve this, but of course what we really care about are numbers. We want to be able to compute numbers that can then be compared with other results. So to do that, I am going to export this photometry data to a file. So you can go to File, Export. In this case, I'm going to use date, mag, and mag air. So this is going to be a file with 3 columns, and you can choose a delimiter. In this case, I will use the tab delimiter, and I could also choose the date format to be either the regular Julian date, the geocentric, or I could choose heliocentric. Either one will work fine. And I can click OK and then give it a file name. And so this will just be wasp12b.txt. And so now I have saved that file. The next step, if we were doing a minor planet, again, where you would basically have a light curve and then compute its rotation period, you could do all of that within Tycho, but this is a exoplanet. I do not yet have a module to generate numbers and transit data for an exoplanet. So instead, there's actually a very nice website out there that does that for you, and so that's what I will be using. So let's go ahead and take a quick look at that. Okay, so if you just type into your favorite search engine, exoplanet transit database, the first result should be what you want. So if you click on the link, you should get this web page here. And what we care about is model fit your data. So there is a link to that here. And it is going to prompt you for the exoplanet in question. So you can scroll through this list here. And again, this is WASP12b. So here it is in the list. And then it's going to also ask for the data file. So I can click on Browse, and I gave it a name of wasp12b.txt. And also the Julian date format. So again, I exported the data and I used heliocentric format. Again, either one will work just fine, but you just have to make sure that you exported it in the same format that you specify here. Brightness column is in magnitudes. So at this point, I can click on Continue. And it is now also going to prompt for any other parameters that I might want to change, but I just like to use the default settings here. So I click on Compute, and it is going to come back with the results. So this is the result of the model fit, and this looks pretty good. And again, what we really care about is this number here. This is the midpoint of the transit, and so the value here, again, I'm just trying to answer that question. Does the alignment have any noticeable impact on the accuracy of the photometry data? So this is one way to potentially answer that question, is can we achieve the same or better results as other well-known accurate photometry programs? So if we look at the guide here, again, this is from Dennis Conti, who is actually the chairperson of the AAVSO for exoplanets. This is he knows his stuff quite well, and he wrote the guide. So his results here, basically, if you look at this table, he came back with this value for the transit midpoint. So if we zoom in a bit, I can show you that. So the model fit time that he had was 0.60123, and the predicted, or the truth value, if you will, if you wanted to call it that, was 0.60190. So if we take the delta between the two, multiply by number of seconds in a day, that's 57.8 seconds is the approximate difference of 1 minute. So that's what he achieved there. Now again, if we look at our value, we can do the same thing. So keep in mind his was around 57.8, and here I've got a delta of 32.8. So in fact, not only are we able to get comparable results, but they're actually, at least on this one particular data point, there's, you could argue that this is just one data point, but nevertheless, it is showing that we are able to get, in fact, slightly better results. So this is basically, again, we're using the same aperture settings. So identical aperture settings, identical comp stars, and we are able to achieve, in this case, even slightly better results. So I would have to say, just based on this, it is certainly possible to conduct very high accuracy photometry regardless of the fact that you have done an alignment routine on the data set. In fact, I would take this a step further, and I would argue that there are in fact other factors that can play a heavier impact to these results. In fact, what kind of star catalog you use, what kind of comp stars you use, what kind of aperture settings you use. So changing any one of those, even just by small amounts, can actually impact your the number you come up with here. So if you want to, we can go ahead and take a look at that. So in that guide, there was no mention of what star catalog was used, only which comp stars were used. So that being the case, I wound up using the Atlas star catalog. So that's what I used on that first pass, and that again achieved a slightly better result than what was achieved in that guide using different software. But what happens if we choose a different catalog? In other words, would we potentially have a more noticeable impact than could potentially have been the case with alignment? Or what, at least what impact would that have? So if I choose the APAS catalog, I'm going to use the same band, the V band here. Click OK, and what I can do is just go ahead and I'm going to use the exact same comp stars, same aperture settings. The only thing I've changed here is the star catalog. So I can go ahead and go back to create photometry from markers, and it's going to go through the same process again. But you'll notice we have a slight difference here now. The median magnitude is a little bit different. And so I'm going to remove that first set here just so I can export this second one. So go to File, Export, and I'll use the same settings here, click OK, and this time I will just differentiate it. This is going to be with the APAS catalog. So I can click on Save. And as before, I will select the data file. So scroll down to WASP12b _ APAS. And in this case, same settings. I'm going to use heliocentric as before. Click Continue. And just to see here if there will be any noticeable difference between having used the Atlas versus the APAS catalog. And as it turns out, there is a difference. So midpoint now is 0.60039 compared with 0.60152. So if we take that delta, again the predicted value is supposed to be 0.60190, and then subtract from that what we came up with here with the APAS catalog, multiplied by number of seconds in a day. Now we have 130 seconds as the delta. So basically we went from having essentially this 32 seconds was what we were able to achieve with the Atlas catalog, and the guide from Dennis Conti was 57 seconds. And now using a different star catalog, we came up with 130 seconds of difference from the computed value here and the predicted. So all this is to say that there are obviously other factors that could play into your accuracy. And now I won't even go into any sort of debate as to which catalog is better. Maybe sometimes APAS is better, but ultimately I think from this we can certainly conclude that alignment in and of itself, and again this goes back to what was stated here, is that if your data is not undersampled, well, here we have a plate scale of 0.57 arc seconds per pixel. That's certainly not undersampled. So if it's not undersampled, then the consequences are expected to be negligible. So I hope that at least this is a starting point to understanding, again, that alignment, resampling in general, if done properly, is next to zero impact. That there are other factors that are much more contributing to the accuracy or the impact thereof. So thank you for watching. See you next time.